times log n over n, then random graph G and P will contain many, and many means actually something like maybe, okay, n to the c or n to the 1 minus c, one of these, let's say n to the c, isolated vertices with high probability. But this is actually a simple calculation that you can verify with the second moment method. Let me not verify it right now, but you can show that if your probability P is below some constant, small constant times log n over n, then you will have this fairly big n to the c size subset of vertices for which there's no edge coming out of these vertices. But even if you have just one of them, of course, you cannot have a perfect matching. And in particular, this gives us another argument to show or to observe directly that the threshold for the family of perfect matching has to be at least of order log n over n. But in particular, it has to be separated away from the expectation threshold by a log n factor. And it turns out that, well, once you move to spanning structures like the perfect matchings, hypergraph perfect matchings, spanning trees, Hamiltonian cycles, or these general types of spanning structures, then in many, many cases, you will have an obstruction that is local, that is very much similar to these isolated vertices, obstructing the existence of the perfect matching. And in many of these cases, what will happen is that you will observe this separation of the threshold from the expectation threshold by this log factor. So we're going to have a break today. Oh. Let's get to the punchline today. Okay, so I mentioned similar log n gap for many other spanning structure. That was one motivation for Khan and Kalai. That's on ID. Yes. To pose the conjecture in the absolutely general context. So Khan and Kalai propose the following conjecture. In 2006, where actually determining the threshold of a lot of the interesting spanning structures, well, not the perfect matchings, turns out that, so for the perfect matching, we do know from quite a remarkable proof of POSA in the 70s, 80s, that the true threshold is indeed of order log n over n. But exactly because of this log n factor gap, this has to be an interesting proof. This makes use of interesting combinatorial property in order to arrive at this bound on the threshold. We know that we can't really use first moment or some type of second moment method directly to arrive at this type of bound, even just for the family of perfect matching. And for many of the other more complicated spanning structures, where it's harder to get directly to them combinatorially, the determining the threshold is open, but the log n factor gaps is kind of the same for many of these examples. So Kai and Kalai propose that perhaps it's true in absolute generality that there is some universal constant C, again, does not depend on anything in the statement of the conjecture, such that, okay, let me state it first in this form. The threshold of any monotone property is bounded above by the expectation threshold. We may have this log factor, where log carries the cardinality of the ground set on which you are working. And of course, we have this trivial lower bound. So in other words, you can describe the conjecture this way. As long as you assume that you have a family strip H of sets that is not piecemeal, being not piecemeal is the nice assumption, why I wanted to write the definition of the expectation threshold earlier this way. If H is not piecemeal, then if you sample a random subset of the domain X with probability C times P times log X, then it will contain one of the set from H with probability at least one. Okay, so this of course would be powerful. So in any specific situation, it would imply directly the correct order for the threshold of several interesting properties. And okay, this next time I will give you the proof, but also after mentioning some further connections of this conjecture. So this is in joint work with Genome Park. Appears just last year. That this conjecture indeed this is true. And we will actually prove the following slightly more precise version. So the statement is if H is not piecemeal, and let this parameter L be the maximum size of a set from this family strip H, then X CP log L, again C is a universal constant, will contain at least one of the sets from H with high probability, with probability at least 1/2. Okay, so in particular, of course, the size of any set in H is at most X. So this is a stronger conclusion than what is asked for in the Kankali conjecture. Also, for example, if you take H to be the family of all copies of this fixed size graph H, so all of the sets in H have a bounded size, then you see that we do not need any additional log factor. And it's true, we saw that the threshold actually matches with the expectation threshold in these cases. Okay. So we will prove this next time. I do have 5 minutes. So I will perhaps we just give here quick discussion of some of this immediate application, and we'll see more interesting application next time. So here are some of the immediate corollaries. And so again, for historical context, one of the interesting cases is when you now take X, for example, to be and choose R. I think R is a fixed constant, like 3. And this corresponds, so XP would correspond to a random Edish-Renyi hypergraph, R uniform hypergraph. in this context, you can take the family H to be generalization of the perfect matching we look at in the graph case. So R uniform perfect matching. And Shamir in the 80s asked to determine the threshold of this family of hypergraph perfect matchings. And even for three uniform hypergraph perfect matchings, they behave very differently from perfect matchings, right? So they are NP hard to find in general. And for exactly these reasons, we can't really get the direct way to find these hypergraph perfect matchings, and determining their threshold is hard as a result. But then, okay, so we do know from a remarkable proof of Johansson, Kahn, and Wu, 2008, that the threshold for D is of order log n times n to the 1 minus r. And let me say here that it is actually very easy to show that the expectation threshold is actually of order n to the minus 1 over r. Okay, why is this? Well, for the lower bound, you can just directly evaluate again. CP of H is very easy to count the number of R uniform perfect matchings. And so you can easily get a lower bound on the expectation threshold of this order n to the 1 minus r. If you want to get the upper bound on the expectation threshold, again, I will say a little bit more next time about a general way to get at it. But we can use the same argument that we discussed before, because we can count these R uniform perfect matchings so easily. You can show that if a family script H cannot have a small cover, because each single set in the cover can only cover a small fraction of the total number of R uniform perfect matchings. So if it has a small cost, you can show that they cannot add up to cover all of the perfect matchings that you need. That gives you a way to certify an upper bound. And in particular, this simple counting argument through the Kankawai conjecture would directly imply the correct order of the threshold of this family of order log n to the 1 minus r. And you can recover that result immediately. And then there are other type of spanning structures that you can look at. So for example, if you go back to the random graph setup, then a classical question is when this family H is the family of all copies of a fixed bounded degree spanning tree. And can ask for the determination of the threshold of a fixed bounded degree spanning tree in the 90s. And this was resolved in the end by a beautiful argument of Montgomery using the absorption method, fairly technical. And this is in 2019. He determines that the threshold for this family is of order theta of log n over n, where this depends on the maximum degree that you are looking at. And again, maybe I'll quickly say how next time. The expectation threshold for this family is easy to determine. It is of order exactly 1 over n. And so if you want to get this order of log n over n, then again, the order for the threshold would follow immediately from the order for the expectation threshold. In both of these cases, why can you get the lower bound on the threshold of order log n to the 1 minus r here and log n over n here? In the case of the spanning tree, we already know the reason why, exactly just because of the isolated vertices. And in the case of the R uniform hypergraph perfect matching, roughly the same reason is why you need this log n factor here. So below log n times n to the 1 minus r, you will find vertices that have no hyperedge coming out of them. So you cannot find a perfect matching. Okay, so I think this is all of the time I have for today. So let's reconvene next time with a lot more connections and then the proof.
There's a question in the chat. The first question is, what about if the property is non-increasing? Do we still have notion of threshold, or is there an example of a non-increasing property with no threshold?
So once you start to look at non-increasing properties, then you could definitely easily write down properties that have no sensible definition of a threshold, because you could fluctuate. For example, if we look at the probability of containing certain graph H as an induced subgraph, then as the parameter when p is 0, this probability is 0, and when p is 1, this probability is also 0. But in between, you could have a point where there's positive chance that you get an induced copy of A. So there's no clear way of making sense of a notion of a threshold in these cases. Admittedly, there are many cases where the property is not strictly monotone, but for which you still roughly have this expected behavior that we saw when we draw the curve of that we defined the threshold before. But right, so but we say that if we want to make an absolutely general theory out of it, then it has to be quite tricky.
What is the general upper bound for that durable cosines? Do you have?
Yeah, so you can work to find the upper bound here. So for example, depending on the regime that we are interested in, so any case, because we will be mainly interested in large structures where this theorem is most applicable, if you send L to infinity, then this constant C can be made to be something very reasonable, like 3 to the 0.995. And that will come directly of the proof that we will see later. But it's reasonable constant.
Then if we can narrow down the bound for that durable cosine C, then can we find us in some sense some sharp threshold for some several cases?
Yes, that's another interesting question. So okay, so depending on the cases, sometimes so sharp threshold turns out have been studied and somewhat more understood from much earlier, so from the Boolean function analysis and hypercontractivity in the 90s, and then lots of seminal results by Flickert, building on works of other people. We know general conditions that allow us to get sharp threshold, and in many cases, we can kind of, if you want to determine a sharp threshold or a specific point, we can do what we do here to determine at least roughly where the threshold is located, and then we apply abstract conditions that allow us to get sharp threshold. But right, it would also be interesting. I guess we don't have an example yet of really going along this technique and arrive directly at a sharp threshold. That I think might be interesting. But yeah, so far it has been a bit more separated, getting the location of the threshold and getting the sharpness of the threshold.
So you said if our family H is sort of constant size, then this your strengthening actually gives that we can forget about the log factor.
Yes.
Is there any other condition that also gives, like a general condition that gives this also for large structures? So
yeah, so right, so we know some explicit, we can write down, and next time I will introduce to you some explicit conditions stronger than this condition that we are assuming here of H being not P small, that will allow us to remove this log L factor, and that are useful in some of the combinatorial application. There are many, it is very interesting to just understand in general what is causing this log L factor to pop up, perhaps under this more general setup of a family being not P small. Of course, we know that log L cannot generally be removed if we are only making this assumption, but there are many interesting phenomena and many guesses at various tweaks that one can get. And in this case, if one expects to remove this log L factor, but there are lots of open questions on that end. But I will tell you at least one explicit condition next time that removes the log L.
Any other question? Okay, if not, let's thank Hui for the very nice. So tomorrow we're gonna resume around the same time, and don't forget to sign up outside right next to the copy. And Fang, can you count? So please tell Yang Fang to raise your hand.
Recording stopped.
Going for the dinner tonight, okay? I can run to a lunch appointment. I'll try to do it.